we now consider the problem of regiochemistry that I alluded to in the previous lesson. So as we saw, a DCC coupling makes it possible to form a dipeptide. But when you mix two amino acids with DCC, we will still get 4 dipeptides because either amino acid can react with the DCC, and then either amino acid can act as a nucleophile. Okay, so we can get the blue amino acid reacting with the DCC and the red one acting as a nucleophile. That gives us the first dipeptide. The red one can react with the DCC. The blue one can act as a nucleophile. That gives us the second dipeptide. A molecule of the red one will react with the DCC, and another molecule of the red one will act as a nucleophile. That gives us the homocoupled dipeptide. And then similarly, we can get a homocoupled dipeptide out of the blue amino acid, which is the 4th one down. So the solution to this problem is to use protecting groups. We need to protect the amino group of the left-hand amino acid so that it cannot be the nucleophile, and protect the carboxyl group of the right-hand amino acid so that it cannot react with the DCC. Okay, so you see what that looks like in the figure. So we have the 2 protected pieces, and now when you add DCC, only the left-hand amino acid will react with it. Only the right-hand amino acid has a reactive amino group. They will couple together, and then when you remove the protecting groups, you end up with the dipeptide that you want. Okay, so good protecting groups will be groups that can be put on and taken off in high yield under mild conditions. Because anytime you use a protecting group, you are adding 2 steps to the synthesis. So the group that we use for the protection of the amino group is called a Bach group, which is short for tert-butyl carbamate. Okay, so if you take an amino acid that has an amine group on it, we treat it with diterbutyl dicarbonate, which is also known as Bach anhydride, Bach 2O, or sometimes it's even called Bach on. So that then puts the Bach protecting group on. Okay, so from the nitrogen of the original amino acid, we have a C double bond O, we have another oxygen, and then we have a tert-butyl group. So as you can see, the amine is now an amide, so it is not nucleophilic. So unlike regular amides, which will only be hydrolyzed under strongly acidic or strongly basic conditions at high temperatures, a Bach group can be cleaved at room temperature upon treatment with trifluoroacetic acid. Now, trifluoroacetic acid is not a super strong acid, it's what we call a moderately strong acid. It has a pKa of 0, which means it is 50% ionized. So what we have here is the net reaction of the deprotection. So the Bach amino acid reacts with TFA, that's what trifluoroacetic acid is sometimes abbreviated, to give you the amino acid you want. Then the other 2 products, as we will see in the mechanism on the next slide, are isobutylene, which is a gas, and carbon dioxide, which is a gas. So therefore, this deprotection reaction is making byproducts that are easily removed, don't require an extensive purification process, and because they're gases, they escape, and this process is essentially irreversible. So before I get into this mechanism, I just want to take a minute to talk about how we protect the carboxyl group, at least in the context of solution phase synthesis. So an effective protecting group for the carboxylic acid is a benzyl ester. Okay, so it's an ester, but because it's benzyl, what is special about it is that it can actually be removed in a reaction called a hydrogenolysis reaction, in which you react it with hydrogen gas in the presence of a palladium or platinum catalyst. And what that does is it takes 1 hydrogen atom from hydrogen gas and puts it onto the oxygen to make the carboxylic acid, and takes the other one and puts it onto the benzyl group to make toluene, which is a nice, stable, and innocuous byproduct. You can also remove this protecting group under more classical acidic or basic conditions. Okay, so I'll have a little more to say about you doing this in the next lesson, but to finish this lesson, I would like to go over the mechanism of this Bach deprotection, because what this helps you understand is what is special about the Bach group, and most of this is chemistry that should make sense to you. Okay, so when we have a Bach amino acid and we treat it with TFA, the first thing that happens is that we protonate the carbonyl group. Okay, so that's the carbonyl group of the amide. That is the most basic site of an amide, not the nitrogen, as we have already discussed. Okay, so then upon protonating the carbonyl group, what can actually happen is you can have the tert-butyl group get lost as a carbocation. Okay, so we basically made a nice leaving group from the perspective of the tert-butyl carbon. So it gets lost, you make the carbocation, and then instead of putting the electrons onto the oxygen atom, you can use those electrons to form a CO pi bond, and then you can simply break the other CO pi bond that's already there to make a carbamic acid. So now we have to think about what happens to both of these fragments. The T-butyl carbocation actually gets deprotonated by base, and it forms an alkene. The arrows are shown here. And that alkene is, of course, a gas, and that's going to be lost to the atmosphere. Okay, so you needed that tertiary carbocation in order to undergo this initial cleavage, but you also need one small enough that's going to produce a gas at room temperature. Okay, but then what is also left behind now is this carbamic acid, and the left-hand OH is going to be the most acidic due to the closer inductive effect of the nearby nitrogen. So that gets deprotonated by trifluoroacetate, putting a negative charge on this oxygen, and now you lose a molecule of carbon dioxide. Okay, so whenever you can form carbon dioxide in a reaction, you're going to want to form carbon dioxide in a reaction because it really and truly is a thermodynamic sink. It's something that once it's formed, it goes away. That's why it's the ultimate end product of combustion. So you form carbon dioxide, and when the carbon dioxide leaves, you're also cleaving the carbonyl CN bond. You would initially put those electrons onto the nitrogen. That would leave a negative charge on the nitrogen. That's not really a good situation. So what probably happens is you have a molecule of TFA, being a reasonably strong acid, coming in, donating its proton to the nitrogen. So at the same time that you're adding extra electrons to the nitrogen, you're also adding a proton to that nitrogen to avoid the negative charge. Okay, so we now have the neutral carboxylic acid, but you have to remember that since this reaction is taking place under acidic conditions, the amino group is going to protonate one more time to give the protonated amine, which is the form of amino acids that are present at low pH. Okay, so this shows Bach protecting groups, Bach deprotection. We introduced a protecting group for the carboxylic acid part of the amino acid. So in the next video, we'll show how you put all of these ideas together to make a dipeptide in solution, and then we'll talk about how polypeptides are really made using even better technology.